Hello, my name is Berger. This is my submission for Lab 2, Motion of a Falling Object, and of course, Physics 2211 with Dr. Claire Berger. The purpose of this lab is to compare the observed position of a falling object, in this case, a ping pong ball. In order to do so, a video recording of a ping pong ball falling from rest was uploaded to the software program Tracker. Tracker was used to accurately record the ping pong ball's observed position, as shown. In order to gather the predicted motion of the ball, a Python program was created via closed group. In the case of the predicted motion of the ball, two separate motions were ran. One with gravity, shown here, and one with both gravity and drag, shown here. And here you can see the drag force. Finally, the observed position and predicted positions were plotted via Google Sheets and compared, shown here and here. The main physics principles involved in this lab include Newton's second law, which states that the sum of net forces acting on an object is equal to the mass of the object times acceleration, or F net equals ma. Using this base principle, we can rewrite and rearrange a few variables in order to update our position, as shown here, and velocity of our ball, as shown here. While considering the forces acting on the ping pong ball, gravity may seem as a big elephant in the room, but we cannot forget about air resistance, also known as drag. Knowing Newton's second law, the object's position can be predicted via closed script, with and without drag. Here, we see our model without drag. First, we set our object's mass to be 27 grams, and we set our initial position and velocity vectors to be 0. Our time starts at 0, and the change in time is 1/1000th of a second. The magnitude of gravity is 9.8 meters per second. J hat represents the direction of the gravity, which is in the y direction. B is our proportionality constant for drag force, and here we set to 0 since this model is without drag. U represents the weight force, which is equal to the ball's mass times gravity times the direction of gravity. But we must remember that gravity is in the negative y direction, hence this negative sign. As mentioned earlier, B is set to 0 because there is no drag force. Therefore, FD is equal to 0. Altogether, the net force is equal to the weight force. Now that we know the forces, I can explain the loop. Here we set a condition where t is less than 617 thousandths of a second, and I'll get to this number in a second. For each iteration of the loop, the ball's velocity vector is updated along with this position. And this will continuously update until this condition is no longer satisfied. Additionally, for each iteration of the loop, the program prints the position of the ball at its respective time t. Here we can see the program run. As you can see, there's no drag force, and we can see each position. Here we see our program with drag force. The only difference in this program is that B is set to a value. Now, while we're in Tracker, the object's observed position can be manually tracked. See the frame counter, and as we progress each frame of this video, the object's position is updated as seen by the red diamonds. Each of these positions is recorded in the table on the right and the graph above it. Here we can see the final time. Notice that this final time is the same as the loop. Now that we have gathered experimental and computational data, the data can be compared via Google Sheets. Taking a look at the data, we can see that the gravity and drag model, in red, more accurately predicts the observed position of the ball, which is in black, as compared to the model with just gravity, which is in blue. Taking note that the value of B in the code was tailored to the model of the observed data, so the gravity and drag model should be roughly the same as the experimental data. Before explaining the differences in the models, you must understand that the system is the ping pong ball, and the surrounding are the Earth and its atmosphere. The initial conditions are that the ball is drawn from rest at a vertical distance away from the ground. After looking at the system and surroundings, we can explain the difference between the gravity model and the observed position model, which is the black compared to the blue. This would be the negligence of one of the surroundings, which is Earth's atmosphere, which contains air particles that combine to create a net force in a direction opposite to motion. This is known as air resistance. The difference between the gravity and drag model and the observed position model, in other words, the red and black, is a fundamental physics error, which is the negligence of rotational motion. Rotational motion alters the motion of a ball. An easy example of this is a baseball pitch, where a pitcher may choose to create rotational motion in the baseball to curve the ball and throw out the batter's swing. However, with that being said, rotational motion accounts for a very small amount of deviation. Another reason for deviation is likely due to the camera angle, which you can see is not perfectly straight, where the wall is not perfectly horizontal with the floor. Additionally, we cannot be sure that the ball was drawn perfectly vertical, so there are many reasons for this deviation of data. Before concluding this lab, one may ask a few questions about terminal velocity, which is the maximum speed an object can achieve while free falling. This is achieved where the force of gravity and air resistance are equal and opposite in direction, creating a net force of 0, and therefore the velocity is unchanged. One may ask, do these models predict terminal velocity? To which I would answer, no. In the case of my experiment, the ping pong ball was not in the air long enough to reach terminal velocity. We can see in this position versus time graph where the slope of the position is changing at all times t throughout the graph, which means that the velocity is changing, and the object therefore has not reached a terminal velocity. Another question one may ask is if the terminal velocity would be changed if I threw the ping pong ball downward, to which I would also answer no. The instant after the object is thrown downward, the only forces continuously acting on the object are still gravity and air drag, which will lead the object to only meet terminal velocity and no more. That wraps up lab 2 for physics 2211.